Hello everybody, welcome to Electronics with NodeEEBench. Today I will show you about the open source project EEBench, how to measure a diode curve and how to look at logarithmic and linear IV characteristics. So let's start here with the GitHub page where you can get the software for free and where you then can also look at the wiring and at the hardware to need to realize this project. So, as in the mentioned before, you just go to GitHub, go to the code, to the zip file, put the zip file into your C directory, and then you're ready to go first for the simulation. If you have a Arduino Maker Wi-Fi 1010 or a similar product, then you can start the diode measurement right away connecting the hardware. So this is basically the software base. Now let's look at the hardware. So this is a picture of my hardware. On the left side, you have the Arduino Maker Wi-Fi 1010, and you see at the top there are two wires, one for VDD and one for ground for 3.3 volt and for 0 volts. And at the bottom, you have one wire for the DAC and four wires for the ADC. And to be able to easily identify them, there is down here a sheet of paper where all these connections are labeled, and there should be also available 8 digital IOs. You see here this Arduino is put on a breadboard. The signal generator, the DAC AC0, is basically going the orange cable here to this bunch of resistors. All these connections here can be monitored by our oscilloscope, channel 1 and channel 3 here. These are the gray lines at the 1 and the 3. And then I can select with this wire up here one of the resistances from 100 ohms to 1 mega ohm with a factor of 10 to the one diode here, and the diode is then connected down to ground. So then I expect I can measure a diode characteristics. The voltage will be measured directly at the diode here with our channels C2 and C4 of our oscilloscope, and then my current will be calculated with a resistor and the voltage drop along the resistor. So my current will be voltage difference divided by resistance values. So let's see. Basically, this is how it looks like if I attach this paper here to identify the different connections here over the VCC and ground and the DAC0, which will be our AVG in our software, and the C1, C2, C3, and C4 from our software. Good. We have the hardware set up, so now let's look at the software. Before that, the hardware here, I have another electronic explorer where I can do the same measurement with a scope to have a reference that the Arduino is working the same as the electronic explorer and gives reasonable results. So to make this possible, after you wired everything, you have to program the Arduino. So let's go to our file explorer, see where our NodeEEBench is. So you see this NodeEEBench is in a local directory. There is a subdirectory Arduino. There is a subdirectory EEBench. And here, by double-clicking on that after installing the Arduino IDE, you will get then the Arduino IDE. So Here's our Arduino IDE. Um, you have to set it up, the Arduino IDE. First, you have to select the board with the board manager. You can select the Arduino SAM boards, and there you have to select the Arduino Maker Wi-Fi. If the boards manager can install these things, furthermore, you need sometimes some other devices which you will be prompted that the Arduino IDE is downloading this one. After having the board selected, then you and the driver, then the Arduino IDE will look at your Arduino board, and for me it detects the Arduino Maker Wi-Fi at the COM99. So you have the program here. So it's only one file which configures the Arduino to work with NodeEEBench, and I want just to highlight here one of the options where you have your read analog X, where you are reading 4 oscilloscope channels. Sometimes you want to use a PMOD82 to gather the analog data. Sometimes you only want to have the Arduino, and this is basically why the 200 line 208 is active and the 281 is commented out, so there will be no reading of the PMOD82. Good. As soon as you have downloaded everything, you can basically go to the sketch and upload, and your Arduino will be configured. The configuration is done via the USB wire. It's done via the serial interface. This serial interface will be used also from the server to communicate with the Arduino and transfer data. So for this, you have to be careful that your serial interface via the USB is not busy with the Arduino or with the Node.js. So every time after you are doing something with the Arduino, you have to restart your Node.js server. So let's go back to our Explorer to be able to start our server. Okay. So here we were at the Arduino subdirectory. You see the Node and Node modules, which for Windows 11 have everything in there. So to be able to start the server, if you go to the NodeEEBench directory, then you see there is a file NodeEEBench.bat, which will start then your Node.js server. It will invoke this batch file will invoke the Node.js and will invoke the server eebench.js, where the communication with the Arduino is done and with the web server is done. So let's go to the batch file and with double clicking starting it. As you start it, you will see, like here, yes, there will be a command window and it will give you some messages for debugging so that you're sure what is going on and that you can detect it. So here you see, yes, it's starting the node with the server eebench.js. You will be able to contact the host at HTTP localhost 3000, and there is a detection of the COM9 with the Arduino. A user is connected and Arduino serial device is detected. So let's go to our web interface. So this is where we had our tab for the GitHub. I have also another tab with the NodeEEBench. You have here the localhost 3000. You see already the event because I did before a trial measurement of the diode. So this is what we will generate. It is still saved from the last session. As soon as you hit this button here, then you go back to the initial page where you see, yes, you are doing the Arduino Maker Wave 1010, and there is a different configuration described here to be able to measure R2R DAC with a PMOD DAC and a ADC, so similar to our hardware we set up. So, diode curve, IV curve, we need different voltages, so we go to our arbitrary waveform generator, we select a triangle, we want to select that we are able to, since we can go to 3 volts, so our offset is 2 volts, our amplitude will be, no, our offset should be 1.3, 1.65, 1.65. Our value will be 1.65. So we are going here from 0 to 3.3. We see, yes, we are very slow with 20 Hertz for one frequency of our signal. So we need 50 milliseconds to cover this. And then we can hit run and we get a triangle waveform. Good. So we have the triangle waveform set up. So we can see in the command window, yes, there were some commands transferred to the Arduino to generate the triangle. The command is basically down here. As I mentioned, I start with code 0, go to the 4095. My step is 70 so that I can generate exactly this waveform. All the serial commands are listed down here, which are possible and how they are done. There's also in the subfolder documentations on GitHub, there's also additional information available. Good, our signal generator is running. So let's look at our oscilloscope. Okay, so we see our x-axis is not good, so we will do here our 10 milliseconds. We see our AVG, the orange one, and the blue one is our C1, our real measured output signal. And then we can see, okay, we have our C2, which is the voltage after it, a C3 before and C4. So basically AVG, C1 and C3 is the initial generator, C2 and C4 is the measurement, the voltage directly at the diode. And unfortunately, there is still a bug there. So after a couple of times, acquisition is not done anymore. So you see, if I do run and stop, then sometimes I can update it. Okay, and there are some errors in between. Let's see how this develops. Let's see. And I don't know why. Oh, because I am ABG1, it should be able to do a trigger. Okay. Okay, so let's have this one. So stopping this one. Okay, so let's use now the two measurements here to get the IV curve. So we have to calculate our current. I'm using here my resistance of 1000 ohm, 1K, like I did my wiring on my board. If I used a different resistor, I have to change this one. I see that I can have my A as a unit. Unfortunately, I don't have here. Let's do a count here. And now I can see my M4 and my M2. On the right side, I can see also my average min and max to be able to estimate, okay, how good, where should I put my X and Y axis so that I see everything. My second measurement, I will use a logarithmic scale to see basically a logarithmic measurement. And to update this one, I have to run another part here. I will see that my range is, unfortunately, I have to 1 amp range. I have to put it here so that I see, okay, I will get a nice curve there. To see that my voltage here is okay, I need the C2 voltage here, which goes C2, the pink one here. Where's my C2? Here. It's very small, it goes only to up to 0.6, so I should change my range here to 50. No, 50 was too small, to 100 millivolts. So now you see, okay, I'm not overshooting, I'm not undershooting. Good. So now I have everything set up. So now I can activate the XY axis. That's interesting. So on the x-axis should be C2 time C2. Interesting. So, and now I can see, I don't want to see all the voltages. I want only to see the current versus the voltage. So this is basically my graph. I see, okay. Here my current, the x-axis, my C2. Let's do here a nice curve. Here is 0, so I'm going up to my maximum of 660 millivolts here, depending on the voltage drop at my resistor. And there I see my current goes from 0 to nearly, I see it here, 2.4 milliamps. So it's a typical diode characteristics where at a certain voltage a current starts to flow. What you see here in the linear axis looks quite different in the logarithmic scale. So metal 2 and mathematics 2 has a logarithmic scale. So there I can see my equation from the diode, which says, okay, I have an exponential function. So here I can see my exponential function. So all these points are on a linear graph, and I see, yes, if I'm lower than 6.4 microamps, then I get here noise. And it goes up to 2.4 milliamps. And in this range, I see there's a linear relationship as soon as I do the logarithmics. So this is my exponential function. Down here, this is measurement errors. This is basically where I have the limit of my analog to digital converter, so that the voltage drop along the resistance is too small, so that my calculation of my current is minimum and limited by the least significant bit. This is all I want to show you for measurement of a diode. Thank you for your attention.